to this new lesson. Today, we will look at the waste management techniques in agriculture. As we know, farming generates different types of waste, from crop residues and livestock manure to food processing byproducts. If not handled properly, these wastes can become a serious environmental risk. But when managed correctly, they can actually be transformed into valuable resources, supporting sustainable agriculture and the circular economy. Let's explore the main types of agricultural waste and the methods used to collect, store, treat, and reuse them. The agricultural sector produces four main categories of waste: biodegradable, chemical, plastic, and mixed waste. In this chapter, the focus is specifically on biodegradable waste, since it represents the largest share and offers the greatest potential for recycling. The main sources include crop residues, livestock operation, and agro-industrial byproducts, such as fruit peels, seeds, or spent grains. Understanding this classification is essential to design the right management strategy for each type. The field-based biodegradable waste mainly comes from crops and agro-industrial processes. Crop residues, such as straw, stems, and husks, amount to more than 2.8 billion tons worldwide each year. They have potential to improve soil fertility, but unfortunately only a small fraction is reused effectively. Similarly, the agro-industrial waste from fruit, vegetable, or meat processing, like peels, pulp, or whey, can become a problem if not handled properly. If discarded without care, these materials may contaminate water, attract pests, and produce strong odors. However, when composted or processed correctly, they can return to the soil as valuable organic amendments. In livestock farming, manure and wastewater are the main sources of waste. If mismanaged, they can cause severe water pollution, oxygen depletion, algal blooms, or bacterial contamination. They also release harmful gases such as methane, ammonia, and hydrogen sulfide. Depending on their specific composition and moisture content and to the percentage of total solids, these wastes require different management approaches. In particular, the waste may appear as liquids, slurries, semi-solids, or solids. Liquid and slurry manure typically result from the mixture of animal excreta with cleaning water, urine, and sometimes rainwater in intensive livestock system, especially in pig and dairy operations. This type of waste is characterized by a high moisture content, typically higher than 90%, and a low total solids content, lower than 10% normally, making it pumpable and suitable for mechanical handling. The main environmental concern about the slurry regards the anaerobic condition in slurry storage, that often facilitate the production of methane and hydrogen sulfide. Consequently, technologies such as anaerobic digestion, acidification, and covered storage have been developed to mitigate these emissions and recover energy in the form of biogas. Solid manure refers to the combination of animal feces with bedding materials such as straw, sawdust, or wood chips, resulting in a product with a higher total solids content, typically higher than 20%. This form of waste is commonly generated in less intensive or pasture-based livestock systems and is usually collected manually or with basic mechanical equipment. Due to its high fiber and organic matter content, the solid manure is well suited for composting, which stabilize the material, reduce pathogens, and minimize odor and greenhouse gases emissions. Proper composting results in a nutrient-rich soil amendment, contributing to carbon sequestration and soil health improvement. The consistency and composition of manure can vary significantly according to different livestock species, housing system, and waste collection method, and also to the liquid-solid ratio. As shown in this table, the manure from cattle, pigs, and poultry differ in dry matter content, nutrient concentration, and also in pH. These variations are further influenced by the use of bedding, flooring type, and whether the system is intensive or pasture-based. For instance, slated floors with flushing systems produce more liquid manure, while the straw-based housing leads to solid manure. Such differences necessitate species and system-specific management strategies to ensure environmental protection and an efficient nutrient recovery. The agricultural waste management usually follows 6 key steps, starting from production, collection, transfer, and then storage, treatment, and utilization. Let's start with the production phase. The production phase addresses the generation of agricultural waste, focusing on the type and the quantity produced by a farming operation. Waste becomes a management concern when its volume or characteristics pose potential environmental or resource challenges. A comprehensive assessment should consider the waste type, the consistency, the volume, the region, and the timing. Seasonal variation can significantly influence production rates. Minimizing unnecessary waste is essential. For instance, contaminated runoff from livestock holding areas can often be reduced through infrastructure improvements like roofing, gutters, and diversions, encapsulated in the principle keep the clean water clean. Additionally, inadequate maintenance of watering systems and feeding equipment can increase waste level too, making regular checks and upkeep vital. Maintaining detailed records of all assumption, data, and calculation used to estimate current and future waste production is recommended. Collection involves gathering waste from its source to a designated collection point. An effective system should outline the collection method, specific location, timing, and frequency, together with labor requirements and necessary infrastructure and equipment. The collection method can influence the physical nature of the waste. Various technologies are employed for different types of waste. We can see here the closed circuit catenary belts used in fixed stable or riding stable for collecting straw-like manure. Or we can see also here adjustable forklifts with alternating belts and all bathers group. This will facilitate the movement of waste material. And also we can see chain scrapers. They are installed for cleaning feeding lanes and consist of a motor unit, return wheels, and a closed circuit chain driving scraping blades. Rigid-tipped scrapes operate through a traction rod that moves back and forth continuously, powered by an hydraulic cylinder and a control unit. The scraping system can be equipped with straight, flap, or butterfly blades, which are mounted on the central traction body using a coupling system connected to the motorized rods. The system also features an automatic reversal mechanism. The alternating mechanical head conveyor transfers the manure from the barn to the collection tank through a 70 centimeter channel. It consists of a rigid rod with pegs. The sub-creek recirculation system allows the slurry, once properly treated, to be pumped out of the barns towards further processing or directly to the storage facility. The flushing system is commonly used to clean manure lane in livestock facilities. These lanes must be slightly sloped to ensure proper drainage of the liquid waste. The system works by flushing recycled slurry, which has often been pre-treated and separated to remove solids along the lanes using handling blades or scrubbers powered by an hydraulic unit. Flushing systems reduce labor requirements compared to manual cleaning and improve the efficiency and consistency of the operation operating in an automatic way. Different designs exist depending on the farm size or the livestock type. In some setups, recirculated water or slurry is used multiple times, reducing water consumption while ensuring effective cleaning. Proper flow control, and maintenance are essential to prevent clogging and ensure smooth operation. Talking about storage, let's say that it's a critical component in agricultural waste management, providing a temporary solution until waste can be reused or treated. Properly designed storage systems offer flexibility in scheduling downstream activities like field application, allowing waste to be spread under optimal weather and crop conditions. Designing storage facilities requires storage duration and volume, facility type and size, location, installation, and operational costs and changes in waste consistency over time. For crop or horticultural waste, the storage typically involves using barns or covered structures to protect materials from weather exposure and reduce degradation. However, manure requires specialized systems to prevent contaminants from infiltrating soil and groundwater. Common methods include collection tanks could be prefabricated or constructed on site using galvanized or bolted steel, or could be built on a gravel base and concrete slab, equipped with covers to reduce odors and minimize rainfall infiltration. For this kind of construction, it is mandatory to have the access door for total emptying and also the coverage. The main materials employed are reinforced concrete, which provides a durable, impermeable barrier to contain slurry and to prevent seepage. In addition to collection tanks, there are also lagoons. They are large, open-air basins, no deeper than 3 meters, lined with reinforced concrete, geomembranes, or polymeric sheets to mitigate the risk of leaching and infiltration of water. While cost-effective and expansive, lagoons are drawbacks like shorter lifespans, complex maintenance, larger surface area requirements, and an increased likelihood of rainwater collection, which can dilute the stored manure. When sizing tanks or lagoons, we need to consider the number of the animals, the daily slurry production per animal, and additional factors such as the wastewater or the rainwater storage. So the retention time, denoted as RT, is expressed in days and represents the period that the slurry is kept in the tank. The number of animals is indicated by N, while Q is the unit slurry production per head per day, measured in cubic meters. D1 represents the volume of wash water added per animal each day. We also account for the rainwater storage volume, so BP, which depends on the surface area of the facility and the total rainfall over the relevant period. Internal structures such as pillars and pumps occupy a volume denoted by VI, while Vs is a safety volume to maintain at least 0.3 meters of free height in the tank. Finally, Vr represents the residual slurry that cannot be removed by the pump. All these factors are combined in the formula shown on the slide to calculate the total tank volume, ensuring it is adequate for both slurry storage and operational safety. Finally, When storing slurry in tanks, it is important to prevent stratification, which can cause the formation of harmful gases due to anaerobic conditions. To avoid this, a pump system should be designed to frequently remix the slurry for proper circulation. The most commonly used pumps for slurry handling include rotary lobe pumps and pneumatic pumps. In any case, it is crucial that the pump is resistant to corrosion and built to withstand the abrasive nature of slurry to ensure durability and reliable operation. Treatment aims to minimize the environmental impact of agricultural waste through physical, biological, or chemical processes. It often begins with preliminary action like solid-liquid separation to simplify subsequent treatment stages and improve efficiency. An effective planning requires analyzing waste characteristics before and after treatment, selecting appropriate technologies, considering facility sites and location, and estimating installation and operational costs. The choice of treatment methods depends on waste time, regulatory requirements, and farm operational capacity. Combining biological and physical approaches often yields the most effective strategy for sustainable agricultural waste management. Chapter 5 deeply describes the most important pre-treatment and treatment used. An essential phase in the agricultural waste management chain is transfer and field application of organic effluents such as livestock manure or the digestate. These operations, though often perceived as logistical, play a decisive role in determining both the agronomic value of the waste and its environmental implication. The movement of waste from the site of generation, whether barns, anaerobic digesters, or storage tanks, to its final application point, requires careful planning. This process is influenced by the physical characteristics of waste. Liquid and slurry are typically moved via pumping systems, using fixed pipelines or flexible hoses as seen before. Semi-solid fractions may require specialized equipment such as piston pumps or high pressure systems, able of pushing material through enclosed conduits. Solid manure, on the other hand, is often transported using mechanical equipment like conveyor belts, front loaders, or trailer, especially when the distances from the farm to the field are longer. Once the waste has been adequately stabilized and transported to the application site, attention must turn to the method of field delivery. This phase is critical for ensuring that nutrients are efficiently absorbed by crops and are not lost to the environment through processes such as volatilization, leaching, or surface runoff. One of the most widespread systems used is the vacuum tanker, which is able of suctioning slurry into its tank, transporting it and distributing it directly on the field. The tanker may be fitted with different spreading mechanism, and the selection of such attachment has significant agronomic and environmental implication. The utilization of agricultural waste is the final and most important stage in its management, focusing on putting treated materials to beneficial use. When properly managed, agricultural residues can serve a wide variety of purposes and even be transformed into commercially valuable products. These residues can be used as fuel, bedding, animal feed, mulch, soil conditioner, or fertilizer. Common utilization methods include spreading residues over land using specialized equipment to supply nutrients to crops, or producing stable nutrient-rich compost to enhance the soil fertility, or also generating biogas for energy with the resulting digestate serving as a fertilizer. By implementing these practices, farmers can maximize the value of agricultural residues while promoting sustainable farming and contributing to environmental protection. Proper utilization not only reduce waste and support agricultural productivity, but it also helps protect soil, water, and air quality. The steps already described can be applied to different types of agricultural waste. Manure, slurry, and other livestock waste, however, may vary significantly, as each animal species produce manure with distinct physical and chemical characteristics. As a result, species-specific strategies are needed for collection, storage, treatment, and utilization. For example, in dairy farming, wastes come from manure, wastewater, spilled feed, and bedding. Depending on the housing system and the climate, manure can be collected as solid, semi-solid, or slurry, and stored in tanks, lagoon, or stacking facilities. Best treatment may include composting or aerobic and anaerobic lagoons, while utilization ranges from land application to renewable energy and compost production. In beef cattle operation, manure accumulates in feedlots. Management differs between paved and unpaved lots, with attention to controlling contaminated runoff and protecting soil compactation. Once collected, manure can be treated and then used as a soil amendment or for bioenergy. Small ruminants, such as sheep and goats, usually produce drier manure that is handled as a solid waste in intensive system, while in pasture system the focus is on proper stocking density and rotation just to protect the soil fertility. Horses generate manure rich in bedding materials, which is often used in horticulture or mushroom production. A frequent removal is essential to minimize odors and flies, especially in urban fringe areas. In swine production, manure is often liquid due to scraping or flashing system. So it can be treated in anaerobic lagoons to reduce organic load and odor, or composted along with the mortalities to produce safe fertilizer. Swine manure is also widely used for biogas generation. Poultry farming produces nutrient-rich waste. In broilers and in turkeys, manure mixed with bedding to form litter, while in layers it is collected under cages. This material can be composted, applied as a fertilizer, or even used as a fuel. For poultry, the carcass disposal is a critical issue, managed through composting, incineration, or controlled burial. The food processing facilities also generate large volumes of organic waste. These byproducts can be treated in stabilization ponds, composted, or also applied to land, provided strict environmental regulation that must be followed, especially regarding water quality and chemical residues. Food processing industries such as oil extraction or cheese production generate wastewater that are particularly challenging to manage because of their high organic content and to their specific chemical characteristics. Indeed, in edible oil processing, wastewater often contain large amount of oil, grease, suspended solids, and other organic materials. It is usually alkaline and present very high chemical and biochemical oxygen demand levels, which vary depending on the type of oilseed and the extraction method used. Residual oils and fats can form scum layers or inhibit microbial activity, making the biological treatment more difficult. In addition, the phenolic compounds and also the processing chemicals may increase the toxicity. For this reason, oil processing effluents often require pretreatment steps such as the oil-water separation, or the flotation, or also the chemical coagulation, before they can enter to the biological treatment systems. Advanced methods like membrane filtration or the anaerobic digestion are effective not only in reducing pollutants, but also in recovering energy. Thanks to their high organic content, these wastewaters can be used for biogas production, contributing to the circular economy approach. Cheese factory produce whey wastewater, which is one of the most concentrated effluents in the food industry. Whey is rich in lactose, proteins, and fats, which also in this case results in an extremely high biochemical and chemical oxygen demand values, much higher than the municipal sewage. So if discharged untreated, this wastewater can deplete oxygen in rivers and lakes, threatening the aquatic life. However, milk whey is also nutrient-rich substrate suitable for anaerobic digestion, allowing the conversion into biogas. Certain challenges exist, such as high salt levels or residues of cleaning agents, which may need to be diluted or carefully managed to keep biological treatment systems stable. Treatment strategies often combine aerobic and anaerobic processes, sometimes integrated with physical or chemical steps. After treatment, options such as nutrient recovery or controlled land application may be considered, provided environmental regulation and monitor requirements that should be respected. In both cases, turning highly polluting wastewater into a source of renewable energy and nutrients highlights the importance of the sustainable waste management in food processing industries. Thank you for staying with us and keep learning.